So this is a continuation of my previous video on how to import a data set, how to explore it visually, and how to handle missing data. So we're just gonna keep on working on the same data set that we had been working on, specifically the data set that had all relevant data points, um, well, all variables and all rows that had less than 5% that were imputed. So we want to use that data set um, to continue with this next video. Okay, and I actually have it all under here. So just to be sure, let's pull up, let's import the file. Just to be sure that we still have it over here. Actually, you know what? We may not need to do that. I think from the previous video we had filled in complete, which is this right here. 26 variables. And 355 observations, just like the original master data set. So as long as we're referring to fill in underscore complete, we should be good. Just in case you want to double check. Here, let me double check using correct data set. You don't have to do this for the assignment, but I'm just doing it just for the benefit of those who want to be extra careful. Filled in underscore complete. And let's do summary. There you go. Oops. Do that. Okay. So, in contrast to before, we can see that we don't have any missing data. Let's do a quick summary. Now, there are still some missings over here. For question 1, 2, 3, you still see the NAs over here. The reason why that is because there probably was rows and columns that had more than 5% missing data. So those are the ones that we didn't want to touch. We just wanted to deal with those that had less than 5%. So anyways, so what you want to do right now is we want to identify outliers and then examine various assumptions that are typically related to parametric tests, the additivity assumption, linearity assumption, multivariate normality, as well as homogeneity and homoscedasticity. So, to identify multivariate outliers, what we want to do ultimately is we want to run a Mahalanobis so we can get a multivariate centroid, which represents the mean of means. So we can run an omnibus test of to basically detect multivariate outliers. So what you want to do first off is to identify and remove any factor columns, so basically any nominal variables, just as it is shown over here. Pretty much the only nominal variables are the ones that we don't want to include, and this is gender, level, as well as advising, which corresponds to columns 1, 2, and 3. Oops. Complete. Okay, these are the factor columns, gender, level, and advising. And let's remove basically the first 3 columns. Space, that means retain all rows, minus the columns 1, 2, and 3. Okay. And you kind of have a preview there that we remove columns 1, 2, and 3. Now, we're going to run the Mahalanobis. This is a pretty long formula, so I'm going to try to break this down for you. Maha equals to Mahalanobis filled in underscore complete, which is for our data set, excluding for columns 1, 2, and 3. Next line of code is core means. And for this one, just as before, we want the same data set without the 3 columns. And a.rm equals to true. That means we're removing all of the missing data from this calculation. The covariance function. Again, similarly, we just copy and paste this. Filled in until complete, and we'll remove our data by once. So I think I got this right. Let's see. Yeah, I forgot to type in filled in until complete. Okay. So let's do it just gives you a bunch of numbers, which is basically the Mahalanobis value. This is the essentially the distance of each person, and the mean is supposed to give you a sense of how far out, how strange, how weird this person is compared to the rest of everyone. Let's get a summary of the Mahalanobis values that might be more helpful. Summary for the variable Mahal. Okay, there you go. We see the minimum, maximum, the median, first and third quartiles, and number of MAs. Those were excluded from the calculations. So this is all fine and dandy to have the descriptives and to have the Mahalanobis values for each person, but we want to have some type of cutoff score for us to figure out who is far away enough to be considered really, really weird that we might want to not include in this data set. Okay, so to calculate the cutoff score for p less than 0.001, because p less than 0.001 is going to be our score. Cutoff goes to squared, and this is 0.999 because it's basically 1 minus the p-value of 0.001, and col, and you want to enter in the name of the data set, again without columns 1, 2, and 3. N col is basically going to count the number of columns in your data set, excluding for this tree, of course. And this is basically going to be the degrees of freedom for this cutoff score. And that. If you look at cutoff, the cutoff score for p less than 0.001 with a degrees of freedom of probably 23, because that's the number of variables, the number of columns, is 49.728. So any person who has a Mahalanobis value bigger than 49.728, we're going to remove them from the data set. Let's do this. Let's check out the number of people who have Mahalanobis values less than the cutoff. Okay. And 243 people had Mahalanobis values less than the cutoff. That's why that's designated as true. And 29 of them had Mahalanobis values larger than the cutoff. So to answer the next question, the short answer is 29 people had Mahalanobis values that exceeded the cutoff scores. Okay, so now we want to remove them. Quick note over here. If you're doing this together with someone else, because your data set was multiply imputed from a distributional source, your final results might be slightly different from another person. So I actually ran this 1 or 2 times, or 2 times actually. And in the first iteration, it suggested that I think 29 people, or was it, 30 people had exceeded the cutoff scores, and I think it's possible for it to have maybe 28. So I mean the results may slightly differ, but it's not going to be crazy different. If you do come up with very different numbers in terms of people who are multivariate outliers, then someone did something wrong somewhere. So to get rid of the multivariate outliers, make a new data set, so no outliers, and then we'll take the filled in complete, whereby in terms of the rows, we'll only take those who have Mahalanobis values below the cutoff, and we'll take all the columns. That's why this is going to be blank. Okay. So we're done with outliers. That's how you identify and remove multivariate outliers. Next is to examine the additivity assumption. Additivity is basically if you have several predictors in your, say, regression equation, you want your variables to not be too similar with each other, because if your predictors are too similar with each other, we have a problem called multi-collinearity. That's usually when your correlation with another variable is more than 0.90. If it's more than 0.95, that's singularity. That's even worse than multi-collinearity. So additivity is basically the assumption that each of our variables does provide something above and beyond than what can already be explained by other variables. When it comes to factor analysis, obviously you'll want your variables to overlap, especially if they are loading onto the same factor, but not too similar, if at all possible. Another thing about this is also basically to test a lot of the assumptions under parametric tests. We're basically going to be testing for additivity, we're going to be testing for linearity, normality, homogeneity, and so on and so forth. If you're running a regular regression, so you're not doing a factor analysis, you can run the real regression analysis to get a lot of the information that you need to test those assumptions. But if you're running something like an ANOVA, a t-test, a correlation, you can use this. And as far as I can tell, if you're doing like a factor analysis, this is one quick and easy way for you to actually check these assumptions as well. And the purpose of checking these assumptions is really to get to know your data. Because really at the end of the day, when you run your analysis and you get your results, if something is funky, something is weird, especially, it would be nice to have all of these additional information to be able to diagnose what might be the problem. So this guide is basically a global screen of assumptions. It's not specific to any one analysis, and so we're gonna basically make a quick regression and get the relevant indices. So back to additivity. So if you don't want to have variables that are too similar to each other, what we can do is basically run bivariate correlations on all relevant variables. If scores are too high, if they're correlated too strongly with one another, you could combine them or just dump one of them, essentially. So let's do correlation for no out, because remember, no out is the data set that had the multivariate outliers removed already. Retain all the rows of participants, but we want to dump 1, 2, and 3 for the columns. Again, use pairwise elimination for missing data. And then relations is going to be and use power. Okay. So if you run this, you get all these bivariate correlations. If you run the second line of code, we're basically going to make a variable called correlations, because this has helped us in terms of making a table. Because as you can kind of see, it's really hard for you to figure out what's 1 and 0.9 and 0.95. So let's just have the computer do it. So to make a table to identify correlations that are higher than 0.90, this is a synnum for symbols for numbers, and let's do this for correlations that we just made. Okay. So how do you interpret this? So you have, just like the bivariate correlations table, y-axis and x-axis are going to be your variables. And there's a legend over here. So if it's 0, then it's 0. If it's okay, let's just interpret it from this for this way. If it's 0.95 and above, it's going to be B. If it's 0.90 and above, it's going to be this star over here. And 0.8 to 0.9 plus 6 to 0.8, it's a comma. 0.3 to 0.6 is going to be a period. And 0 to 0.3 is just going to be nothing. So what you're looking for is essentially this asterisk over here, or this star, or this asterisk, and any beats in your bivariate correlation table. And looking at this, I don't see any asterisk or B. So, again, if you do come across any really high correlations, you can either combine these columns or just remove any one of those variables from the final data set. So, oops. So provide interpretation, additivity assumption is met, no multi-linearity because no bivariate correlations equal to more than 0 between all items. Okay. Like the final data. So this would be if you had to combine any columns, you want to make a final data set that does not have any redundant variables or any redundant items. So let's just follow through. Let's just call this no out final equals to no out. Again, if you do have any columns that you do want to remove, you can add this into this code. But let's just, oops, I forgot to add a chunk. There you go. Final is going to be no out. So we're going to work with final from now on. Next, we're going to examine the linearity assumption. That is all combination. So multivariate linearity is the assumption that all combinations of the variables are linear. If this analysis goes really bad, you can go back and check the bivariate scatter plot to see if it's one variable or something. But to do a multivariate check, we first need to make a fake regression. To make a fake regression, you need to create random chi-square values for the same number of participants in your data. Because for many of these assumptions, like linearity as well as normality, homogeneity, and homoscedasticity, the errors should be chi-square distributed. So you want to create a random chi-square with the same number of participants as our data. So the code is going to be random equals to r square. N row basically means the number of rows, so that equals the same number of participants in our data set, which is the final data set that we just named. And then 7 is just going to be a random number, which is the degrees of freedom. Usually, I'm trying to think of the range that would typically work. Anything above 2, I think, works. So, again, because we are creating a random chi-square values, we're using the same number of participants, that's n row from the data set, but with a degrees of freedom that is just going to be random, so more than 2. Okay. So next, you want to run a fake regression with the random chi-square values that was just produced as the DB, as predicted by all of the relevant variables. So items 1 through items 23. So we're going to use the LM function in order to do this. Typically, if you're in t-tests, for example. If you're running a t-test, you say y tilde x. That means y is predicted. You're using x to approximate or predict y. But for this one, because it's random, we're going to do random tilde period, because period basically means all of the variables in the data set, which is nice. So that means you don't need to type every single variable in there, and the data is going to be the final data set that we just made up. So let's run this fake regression where we're using all of the data, all of the variables, predicting a random DB from the final data set. Okay, so run the fake regression. Based on this fake regression, we want to produce studentized residuals or standardized residuals. So standardized studentized based on that fake regression. And then we want to make a QQ plot integrated with a straight line through the plot. So this will help us examine the linearity assumption. QQ norm, standardized. So this came from the standardized residuals. And let's also add a line, a straight line, to the QQ plot to help us examine this better. Alright. So here's our QQ plot, and if we were to add this straight line, Alright, I figured out what was going on before. So I was getting an error message because the QQ plot was not coming up over here in the plot window, but it's coming up in over here in the place where you would put in the code. So it turns out that for some reason something had changed in the code over here. So if that ever happens to you, go to R Markdown. So this is something specific to Markdown, and it was actually, this checkbox was actually ticked. It said show output inline for all R Markdown documents, which I think it forces all output, including graphs and tables, to be all in the R Markdown document when you're working on this in Studio. So I went ahead and unchecked this, and that seemed to fix the problem. So let's try this again. So this is the QQ plot, and you can zoom in right here. And basically, what we want is we want these standardized values to be pretty much in a straight line, especially the ones that are between 2 and -2 in terms of their standardized values. And so to help to see if this is a straight line, I went ahead and add this in, and there you have it. So this is actually pretty good. So in terms of whether the linearity assumption is met, the QQ plot suggests that hold on. And just to give you some context what this is, the X-axis are the actual z-scores, the studentized residuals. Oh, sorry. Let me take that back. The x-axis are the actual z-scores, and the y-axis are the residual standardized scores. And so the residual is the distance between the standardized scores according to the regression line, and the x-axis is the actual z-scores. And so basically you want your data to not deviate to not deviate in any kind of pattern across all values of the z-score. So you want most of the data to be around 0 over here. So the interpretation is linearity assumption is met because according to the QQ plot, most of the, and say most, I'm talking about plus minus 2, most of the z-scores appear to be around 0. Well, they seem to have close similar distance across all values. Okay, next is, let's take a look at multivariate normality. Realistically, in practical terms, as long as your sample is fairly large and the rule of thumb appears to be more than 30, normality really shouldn't be a huge concern over here. As long as we have enough people to meet the central limit theorem, normality is not so much an issue compared to other issues such as being a multivariate outlier according to the Mahalanobis distance. So outliers are a more pressing concern compared to normality. So I'm going to show you really quick on how to examine multivariate normality. First off, you want to make a histogram of standardized residuals. Histogram. Oops, forgot to add a chunk. Histogram. Standardized breaks equals to 50. And you can play around with this too to get what looks the best. And let's zoom in over here. So in this histogram generated over here, in terms of the standardized, hold on. Yeah, in terms of these standardized residuals, what we want is we want most of the data to be around 0, which appears to be what it seems to be. Most of them are pretty close to 0 here. What would be a problem is if we had the distribution be negatively skewed over here or positively skewed over here. So normality assumption is met. Most of the standardized residuals appear to be around 0. And between plus minus 2. Plus minus 2, plus minus 3 is the range that we're looking for, and most of it, and we want most of them to be close to 0. All right. Homogeneity and homoscedasticity, both concepts are fairly closely related to one another. Homogeneity is the assumption that variances of the variables are roughly equal for all of the variables. And heteroscedasticity is the idea that, or homoscedasticity is the idea that the spread of the variance of each variable is the same across all values of the other variables. And so when I show you a picture in just a little bit, in a bit, hopefully that'll make a little bit more sense. So first of all, we want to make a scatter plot of standardized fitted values, which are basically the predicted scores for each person, predicting the standardized residuals. Okay. So fitted equals to scale for the fake regression. So basically what we're doing is ultimately what you want to do is that we want to make a scatter plot of residuals where the x-axis are going to be the standardized fitted values. So in other words, the predicted scores for each person according to your fake regression. And the y-axis is going to be your standardized residuals. So this is the difference between the predicted score and the person's actual score in that regression. So in other words, sometimes we call this as y minus y hat. So let's make the y, which is what this formula is for, and then let's plot the y with the y hat, predicted score. Okay. Let's zoom in. Okay. And so again, the x-axis is going to be the predicted score for a person. These are standardized fitted values, and the y-axis is the difference between the predicted score and the person's actual score. Standardized, of course. Let's make some lines over here across the x-axis and the y-axis, just to make some quadrants that might help with interpretation. So AB line, 0 and 0. Let's do that's weird. I wonder why. Let's do v equals tree. I forget which is. Oh man, what did I do? Tree. There you go. Sorry about that. Okay, let's just try to ignore this for a little bit. So in terms of homogeneity of variance, you want the dots to be equally spread across all 4 quadrants right here. So 1, 2, 3, 4. You really don't want any clouds or any spots to hover over just one spot, because basically you want the each person's variance to be equal across all values of whatever that variable is. For homoscedasticity, you basically don't want any particular types of shapes. And so if you were to say draw like an imaginary line, especially, so let's just focus on say plus minus 2 and plus minus 2 over here, and we could actually do that. Let's just see if I could. Let's plot this again. Okay. Let's do AB line V equals 3. AB line V equals, actually, why do I keep doing 3? 2. Negative 2. AB line H equals to 2. And AB line H equals to negative 2. Do that, and then that, and let's just add the rest of this. Perfect. Okay. So you don't want any types of shapes, so you want most, so basically you want most of the dots to be equally spread across all 4 quadrants, which seems to be what it is over here. And then homoscedasticity, you don't want any particular shapes. I mean, one way, and you don't have to do this, one thing that you could do is you could take this picture and then say, let's open Word, let's paste this in Word. Oops. There we go. So, try to draw a line over most of the dots. So here, so let's say insert shapes. Maybe one. Where is it? I think it's this one. Oops. Let's do that again. So. You're always going to have people out here that are just outliers, but let's just focus on most of them, especially this area here. Okay, so basically what you don't want would be a very, very obvious shape in any one of these quadrants in any type of direction. You want them to be pretty much equally spread across all 4 quadrants around the 0, y, and x axis over here. Let's go back to our studio. And is on scatter plot. Let's standardize for the values, predicting, standardize residuals, homogeneity and homoscedasticity assumptions seem to have been met. And that's how you check for homogeneity and homoscedasticity. Just a quick tip over here, especially for normality. Transformations are definitely things that you could do if you find that your data is not linear or not normal or doesn't meet any of the assumptions for homogeneity and homoscedasticity. A lot of times those transformations could be more troublesome than helpful. One way one thing that you could do is you could run the analysis with and without the transformation. If you want to demonstrate that, hey, like either way, it doesn't really matter if you transform or not, because for the most part, like I said, especially for normality, for example, if you got a large enough sample that helps you approach the or meet the central limit here, you probably should be good. Main reason why I do these checks is again to get to know my data. That way, when I get the results, I kind of know what may be wrong somewhere. If I do come across any types of results that are just unexpected, and that would require some explanation that is beyond the prevailing theory of what may be going on with the data. So it's good to check these assumptions, just so that you can get to know your data more intimately and to better able to diagnose things as you run along with your analysis. So that is all, and thanks for watching.